day before spring break, or we can take it after spring break.
After like that.
No.
So obviously, the quick pro to taking it before is when you're in Cancun and you don't have a black cloud of having to study everything.
Let's take a vote. Let's take a vote.
Yeah, so we are going to vote. Obviously, I'm going to go over some quick pros and cons. If we take it before, then after spring break, you're just chilling on a beach.
On the beach. Of course, the beach.
A con is you don't have more time to study. However, it is time that we're not in class studying. So,
Supposedly.
so quick vote. Raise your hand if you would like to.
When is spring break? So when
Starts
So we have-
after this class, like on the 14th.
when will we have to test?
So it would be next Friday.
Next Friday?
So we would have 3 lessons this week, Monday, Wednesday, Friday. Half a lesson on Monday. Start reviewing with a project. Review. Take the exam Friday before spring break.
Or take the class so we come back.
It won't necessarily be the class we come back. It would just be after. The problem is after a week of not meeting, a lot of stuff feels very.
Yeah, a lot of stuff just drains out your ear, you know, and it's forgotten forever.
And then it's like, oh no, spherical coordinates. So that's what we did weeks ago. So what are you guys thinking?
I go with the crowd, whatever y'all think.
Tanner?
I would normally say let's take it the 14th, but it's my birthday and I'd rather just start spring break.
This weekend.
Oh, it's really close to your birthday.
I go with the majority. 'Cause I see it from your aspects.
I'm like, I can use more time to study. I won't be taking an exam on my birthday.
Yeah. Professor, the baby, and I see it from your aspect that we need to, while it's still fresh in our head, go ahead and take
Just
it.
keep it fresh.
But
Keep it
I
new.
understand
Look back
of
on the
wanting to
progress.
go for spring break and so whichever way y'all want to go. What y'all think, people? What are we doing?
I think after.
That's one vote for after, 2 votes for after, 3 for after. Uh-oh.
It is after.
Chloe's
Yeah.
the only one.
It looks like after.
Let me text you. She's texting me right now.
What's your vote? Yeah, I'm the same way. I mean, so
Tanner's like, I'm gonna ace this either way.
exactly. Exactly. Hold on. Smile for the camera one time. Yeah. Mr. Math Wiz over there.
I will be doing Tempest. I love this stuff.
Alright, so this is just a quick warm-up before we start, and I wanted a chance to see some interpretations with some word problems. Before we actually do that, I will do a quick Calc 1 example just so we can remember.
Oh shoot! No. Come on, work with me here today, please. There we go. Now focus. Wants to act up today. Oh, there we go. I had it in there crooked. Okay. Perfect. Uh-oh.
So this is just one of the problem types that we saw in Calc 1. It was, what if we have a table of data where I have t measured in minutes, and I have s of t measured in students. So far we've only been seeing things written as formulas, but it's very possible that you see a table of data. And we have a prompt that says the number of students in a room after t minutes is modeled by s of t. So it's just giving me this many minutes go by, this is how many students are left in the classroom. So we want to approximate s prime, so the derivative at 2.5, and interpret its meaning in the context of the problem. So looking at the table here, I want to approximate the derivative at 2.5, and you just have to do the best that you can. These are 2 points that are on the function, on the curve, so I have to use the coordinates 2, 10,
Oh,
and 3, 9. And I can approximate the rate of change or the derivative by just finding the slope of the line between those 2 points.
Oh, wait, no, which is -1 there.
So first, any questions on just the actual value before we try to interpret it? All right, who thinks they've got a sentence that would interpret what is s prime of 2.5 being -1 to mean in this context?
At t point, yeah, 2.5.
Yeah, exactly. It's saying at t equals 2.1, I like that we're already hearing the word decrease. That's what the derivative means for us. At t equals 2.5, the number of students in the room is decreasing, because my derivative is negative, at a rate of 1 student per minute. So the derivative being negative means that our function is decreasing. Our function is outputting the number of students. So that means the number of students is decreasing at a rate of 1. And then the units of the derivative are the units of the output divided by the units of the input. Students per minute. All right, we're going to do the same exact thing now. Looking at a table of data. So if we were wondering what a function would look like word problem-wise, with 2 different inputs, this is both a good kind of story to kind of match it, as well as being able to interpret partial derivatives. So it says the differentiable function r of s comma c, so function that inputs an s and a c, gives the flavor rating on a scale of from 0 to 100 points of a cup of coffee made with s packets of sugar and c ounces of cream. Select values of this function are provided in the table for select values of s and c. So just making sure we understand how to read this table, it's kind of written like S/C, where S is going to be all of the values in the first column here. And reading horizontally, these are going to be all the different values for C. So question 1, evaluate R of 2 comma 3. So before I even think about what this means, what is R of 2 comma 3? Yep. This is saying if you have an S value of 2 and a C value of 3, you get 88. So who wants to take a stab at it, interpreting what R of 2 comma 3 equals 88? What does that mean in the context of this problem?
A coffee with 2 packs of sugar and 3 ounces of cream has a rating of 88.
Perfect, yep. So a cup of coffee made with 2 packets of sugar and 3 ounces of cream and a flavor rating of 88. So now, pretty good with that so far. This is the new piece for us. Use values in the table to approximate the partial derivative at 0, 2. But I'm going to pay attention to the notation here. This partial R over partial S, that's saying, how is the function changing as you increase S? So we were seeing that last class, it was like, the partial of F over partial X. It's saying as we increase in the X direction. So kind of getting ahead of ourselves with the interpretation, this is now saying as you increase in the S direction, how is R changing? How is the flavor rating? When you go to 0, 2, this point here. 0 packets of sugar, 2 ounces of cream. Now, thinking last time, making sense of this, this was saying if you move in the X direction, that means X varies and Y is fixed. So if I have S down here, this is saying that S is changing and C is fixed. Notice if I move downwards like this, my C value is always fixed. C is always 2. But yet my S is changing. So I need to grab 2 different points here. I need 0, 58. And what's the next point that I'm going to grab? 1, 79. So just to be clear here, these points are S, R, S, R, and now I'm increasing in the S direction, so increased by 1, and now I just want the Y coordinate. That means my partial in the S direction at 0, 2 is going to be roughly the slope there. I've got y2 minus y1, x2 minus x1. And what is 79 minus 58? Please ask questions on just the math here. So one more time, this notation is saying, how is R, how is the function changing if you increase in the S direction? So looking at this table here, S is written in this column, so it's saying if you increase in S, but C is fixed, this value here never changes. If if I increase in the S direction, how is that flavor rating changing?
That's not 29. That's not 29. Yes, 21. Okay, so I can't add a little bit.
You guys pay me to teach you count 3 how to arithmetic. All right.
That's right.
Who can give me an interpretation for what this would mean in the context of my cup of coffee?
So, like, as you change the amount of sugar, the flavor rating increases as a rate of 21.
As long as you have 2 ounces of cream.
Yeah, so we can say
Mm.
increasing the amount of
That's not
sugar
negative.
in a cup with 0 packets of sugar and 2 ounces of cream increases the flavor rating by 21. What are my units here? Points per.
Packet of sugar?
Yes.
Oh, really?
So this is keeping in line with our Calc 1 review over here. The units of the derivative, since we were doing change in y over change in x, then my units there were the y units over the x units. The units were students per minute. The same thing holds true with your partial derivative. The units here of my function's value r were in points, and the units at the bottom were in packets of sugar. So my units here are going to be points per packet, points per sugar packet. Questions? All right. Go ahead and flip it over. It's the same story, the same table. It just now starts off with number 3. So just so we're not flipping it over and looking back at the table. So I'm going to give you guys a couple seconds to work together. This is the same question. The only thing is I wrote a different notation. Instead of writing that partial notation, I just wrote the subscript this time. So I'm going to give you a couple minutes to attempt to do problems 3 and 4. direction a little head start. This is the notation, partial derivative with respect to c. That's saying that c is changing, but s is fixed. So s is fixed, and now I'm going to increase in the positive c direction. So as c increases, that means my points are c, comma, r. So I've got 2, comma, 84, and 3, comma, 72. Now from there, keep the derivative, interpret it. So I've got two different points here. They're both c, comma, r. I can approximate the slope, but I get a negative number. Doesn't mean the flavor rating is negative. It's a derivative. So this is saying if I increase my amount of cream, then my flavor rating should decrease by 12 points per ounce. All I did in the interpretation was I wrote it a little bit differently than the previous one, just to show a different way of writing it. So some way, maybe when we were in Calc 1, we didn't write it as, it decreases by 1 student per minute. Maybe our instructor in our last class said something like, for each additional minute, the number of students decreases by 1. Just writing it a different way so we can see it. So the first part is just the intro, coffee cup with 3 packets of sugar and 2 ounces of cream. Decreases, because the derivative is negative, in flavor points for each additional ounce of cream added. So it's saying if you add 1 additional ounce of cream, then your flavor rating is going to decrease by 12 points. We should say the amount of points. So decrease in, we'll say decreases by 12 points in flavor rating. Yep.
How did you know she used the points 284 and 372 instead of 076 and 182?
I agree with that.
76. So you want to start at the point 32, right?
3, 2. Okay, right.
So it's saying compute the derivative at 32. So start at that point and then increase in C.
Which is
Questions?
4, 3.
So now looking at 4, again, just a different notation. This is saying the partial derivative of r with respect to s at the point 4 comma 3. So maybe in Calc 1, another way that we could have seen the derivative written is you could have said dy dx at x equals 2. That was just another way that we potentially could have written it in calculator. I think when you actually whip out your TI-84 and you go to the derivative menu, this is actually how it's presented. It's got that vertical. So this is, it's just telling you, you don't have to compute anything. Given that the partial of r with respect to s at 4,3 equals 0, interpret what this would mean in the context of my flavor rating for my cup of coffee. So true, this does mean if you have 4 packets of sugar, 3 ounces of cream. What does this mean, my partial of r with respect to s?
A cup of coffee with 4 packets of sugar and 3 ounces of cream does not give anything in flavor point 0. It just stays consistent.
Keep going, you're dancing all
For
around.
each additional ounce, wait, for no additional, oh, actually, no, oh wait, for each additional ounce of sugar.
Packets of sugar, yeah. That's exactly what this is saying. This is saying if you increase in the S direction, so for us, if you add a packet of sugar, the flavor rating doesn't change, is what the derivative equals 0 is saying. If you got a negative number, that's saying if you increase the amount of sugar, then your flavor goes down. If you got a positive number, it means if you're adding sugar, the flavor rating goes up. This is saying at this kind of combination of sugar and cream, if you increase the amount of sugar, then your flavor actually doesn't change at all. So we can say, adding a packet of sugar to a cup of coffee with 4 packets and 3 ounces of cream does not affect the flavor rating. Any questions? Alright, so we do have another lesson that we have to look at. But first, take 2 seconds, take a breather, set a text. We're going to talk about the gradient factor.
Gradient. Oh, we talk about that in physics. I'm not a professor. Gradient.
next thing for us is something called a gradient vector, which just definition-wise, this is saying, a new notation for us, let's call it a nabla, this upside-down triangle. This is saying your gradient vector is equal to a 2D vector. Yes, it's a function in 3D, but this interesting vector that we're referring to outputs a 2D vector, kind of important, where the x component is just the partial derivative with respect to x. The y component is the partial derivative with respect to y. I think we're mature enough now that you might see me start ditching this notation of x comma y. It just gets to be a lot to have to write that every single time. So even looking in the textbook, we get pretty lazy and we can just say this gradient vector, f sub x, f sub y. Means the same thing. So this is saying how much am I changing in the x direction, how much am I changing in the y direction. It turns out when you combine them both into a 2D vector, this vector will point in the direction of steepest ascent. And I'll show that on the projector in just a second. So first thing that we really need to take away and let it need to sink in, yes, this is a 3D surface, f of x, y. But this new gradient vector piece is a 2D vector. So let's go ahead and look at this surface here. And imagine that I'm standing at this red point, and no matter where I move this slider, this vector is always going to point in the direction of steepest ascent. So if you're standing on this point and you're on some sort of hike going up a mountain, this vector is going to point, hey, if you want your walk to be as hard as possible, walk in that direction. Now I've been emphasizing that it's a 2D vector, so the best way to visualize this gradient is to look at your xy bird's eye view. You're going to get a 2D vector, and it's saying if you walk in this direction in the xy plane, then that is going to be the direction that you have to walk in for steepest ascent. So let's actually use this exact surface here. I'll maybe change the numbers just so it's a little easier for us. So go ahead and write down this surface, f of x comma y. Is equal to x squared minus 0.5 y squared plus 1. So if I want the gradient vector, just my definition over here just says make it a 2D vector where the first component is your partial derivative with respect to x. Your y component is the partial derivative with respect to y. So maybe the first thing that I'll do is just compute my partial derivatives.
2x. Y.
Negative.
Negative 1.
Yeah. So just pausing for a second and just making sense of what we're writing on the paper. We saw this last time. This is now a function. You input x's and y's, and it tells you if you increase in the positive x direction, this is how much your z coordinates change. You give me some x and some y. This is saying if you increase in the positive y direction, how is z changing? It turns out if you kind of mash them together as a 2D vector, it's pulling you in the direction of x, pulling you in the direction of y. This is going to be the 2D vector where your z coordinate will have the greatest ascent or change the fastest. So if I want to know how much I am changing at the point, and now you get to pick this 2D point, what 2D point? 1, 1. You're going to get a 2D vector. this is saying if you are standing at 1, 1 in your XY plane, then if you want to walk uphill the fastest, you have to walk in the direction of 2, -1. If you walk in that direction, you're going to be walking uphill with the greatest ascent. And I will double, triple check this on our projector. Move some z coordinates around so we can see a little better. So this is my surface here, and this, we want to move to the point 1, 1. If I'm standing at the point 1, 1, this gradient vector, 2, -1, is the direction that I have to walk in for the steepest ascent. So if I want to make my hike as hard as possible, this is saying walk in that direction.
How do we know to use 1, 1?
So you get to pick that point.
Okay.
And we pick that point just to. How about this, Reginald? Give me another.
4, 2.
You want to throw some negatives in?
Negatives? -4, 2.
So my gradient vector is 2 times the x coordinate, comma,
Minus
the
the
negative
y.
of the y coordinate. So this is saying if you're standing at an input in the xy plane of -4, 2, if you want to walk in the direction of greatest ascent, walk in the direction of -8, -2. Something like that.
Okay.
Now let's go ahead and graph this. Yeah.
Kind of a vector within a vector. Like I'm like thinking of this like tiny little plane to compare your direction, and then like your position is just whatever given points for.
So your position is that 2D plane, but the height or your altitude on your hike is going to be whatever you plug. If you plug this into the original function, you get your altitude and your height. You can think of this as like a northeast-west or northwest direction. That's saying, while standing at that point, if you travel in this direction, that's going to be the direction you have to walk to make your hike the hardest. So if I change this to -4, 2, just changing some stuff. So if you're standing at that point, if you walk in the direction of -8, -2,
Yeah, that's pretty
that is the
good.
direction you have to walk in for the steepest ascent.
Yeah, that's pretty steep too.
Please ask questions.
What's the significance of the steepest descent? Like, is it a tangent line to the 3D shape, or?
So it's not necessarily tangent. Right now it's just outputting a 2D vector of where to travel. Now, of course, the next natural question is, well, what if you want to compute the actual rate of change in that direction? Do we have any kind of natural guesses here?
Change.
Well, we have one point, and it's just outputting a 2D vector of the direction to travel to get the maximum rate of change.
Using that slope, isn't that our slope?
Can I use our tangent plane?
It'll be the magnitude of that vector.
Magnitude. Hmm.
So if I said, here's a surface, you're standing at the point 2, 1, the gradient vector gives you a 2D vector of the direction you have to travel to get the maximum rate of change. So of course the next natural question is, okay, well if I did walk in that direction, what is the rate of change? The rate of change is then the magnitude of that vector. So looking at this example over here, making sense of this point again, this is saying, if you're standing at the point 1, 1, this is just looking down in your bird's eye view. This is saying if you walk in the direction of 2, -1, then you're going to get the maximum rate of change. Okay. Well, then what is the rate of change if you walk in that direction? The magnitude of this vector. And just a quick reminder, that is the square root of x squared plus y squared. Here. This is saying if you're standing at the point -4, 2, you want to know the direction that you want to walk in for maximum rate of change for steepest ascent, and you're going to walk in the 2D direction, -8, -2. And if you walk in that direction, you get a rate of change of root -8 squared.
Oh, -8, I love that. 60.
We're at 60. How it goes. So let's just kind of play around with it for a second. I'm just going to graph some other surfaces, so maybe so we can get a little bit of an intuition as to.
Whoa, look at that, that's nice. Cool.
So you could think of this as an actual hike now.
Yeah, right.
We've got lots of different peaks and valleys, and dragging this gradient vector, this slider around, you can see that this is always going to point in the direction of steepest ascent. But again, the best way to make sense of this and to visualize what we're getting on paper is to just look at the xy view. Because our gradient vector is just a 2D vector. So this is kind of the direction that you're seeing, and it's showing you where to go. So although I have no idea what this surface looks like, this 2D vector that we get on paper just gives you a direction of where to go. Now I'm going to search for some magical points here, and I hope this builds some intuition for our next lesson. What do we think is happening at roughly this point, where my gradient vector doesn't actually point at all?
Flat surface.
Oh, it's
Yeah.
Yeah.
So it doesn't have a slope there, right? Since it's just a straight down.
Or maximum.
So no maximum, no minimum is actually really nice. So let me see if I can manually change those to a point. So notice my gradient vector here is the 0 vector. 0 in x, 0 in y. And yes, we are slowly building an intuition. These are going to be equivalent to the quote-unquote critical points from Calc 1. Because it's saying, oh, if you want to walk in the direction of maximum ascent, but there's no higher that you can get, then that's going to be your 0 vector. And very similarly, if I did have a point that was a minimum, well, then walking in any direction would give me a greatest ascent. Walking in any direction, I've got kind of this bowl of that. So we're going to get a 0 vector there too. So let me ask this question. This is asking, or this outputs greatest ascent, steepest ascent. What if I want to walk in the direction of my least, or my maximum decrease in the rate of change? That's exactly it. If I'm walking in this direction, and this makes my walk as hard as possible, then you're absolutely right. If you want to make your walk as easy as possible, you just turn 180 degrees. So if you have the negative gradient vector, still, again, it's a 2D vector. So just making the vector negative will now point in your minimum rate of change. And if you want to find the rate of change in that direction, just be super careful. It is going to be the negative of the magnitude. Why am I saying careful there? If you found the negative gradient and then found the magnitude, you're actually going to get the same thing. Because notice you take square roots of something squared. So you have to do that, then make it negative.
Because you're getting the absolute value the first time.
Right. Yep. How are we going? This will be the last piece for us today. So we have this idea of a gradient vector. Again, it outputs a 2D vector. And this says if you're standing at this point, walking in this direction increases your rate of change the fastest. Well, thinking about our partial derivatives so far, we've had the partial derivative with respect to x says if you walk in the x direction, how is z changing? Partial derivative with respect to y says if you walk in the positive y direction, how is z changing? Well, a really good question is, what if I just want to walk in my own direction? Right now, the only two directions you have is positive x, positive y. What if I want to walk in this direction here, and I want to know if I'm walking uphill or downhill? But we haven't actually realized that yet. That's the idea of a directional derivative. What if I want to walk in the direction of 3, negative 4? How is my z changing? That's the idea of a quote-unquote directional derivative. So a directional derivative, which we'll notate as capital D, this is saying in the direction of some unit vector. And that is the 2D direction that you want to walk in. So this is a unit vector, and I'm going to underline that. We have to remember that this idea, there has to be a unit vector in the direction
You only have three-dimensional choices to walk in.
Say that one more time?
But you only have three-dimensional choices to walk in. Your x, your y, or z.
So you are actually only choosing to walk in X or Y.
X, y,
So
okay.
I'm always going to make this analogy of the hike again. When you're on the hike, you only get to pick X and Y directions. The Z is dictated already on the hill. Depending on the direction you walk in is how your altitude is going to change. So why we need a gradient vector is part of this definition here. You're going to do the gradient vector dotted with, so dot products aren't going anywhere, dotted with the unit vector that you wish to travel. Yeah.
So it's almost like your y was dependent on your x.
Yep.
Now your x and now your z is dependent on your x and your y.
That's exactly it. Yeah, Z is already depending on your X and your Y. So let's do an example over here. So I have a surface here. Part A, just compute the gradient. So there's no words now. We're responsible for recognizing this nabla. This means gradient vector. My definition over there is it's not too bad. It's just the partial derivative with respect to x as the x component, comma, the partial derivative with respect to y as the y component. So now part B is really honing in on this new piece for us, directional derivatives. This is saying determine if the surface, or you can think of that as the z-coordinate, determine if your z-coordinate is increasing or decreasing in the direction of this unit vector at the point 3, -1. So let me just conceptually make sure we understand exactly what this is asking. I'm going to use that analogy again. We're on a height. We're on a mountain that is dictated by this surface. If I am standing at the point 3, -1, and I choose to head in this direction, 0, 1, my question is, am I going to be walking uphill or downhill? And if so, by how much? How is that different than what we were doing in the past? The gradient vector just outputs. It dictates the direction. If you walk in this direction, your hike's going to get the hardest. You're walking in the direction of steepest ascent. Now you get to pick the direction, and this is going to tell you your rate of change. Now, first of all, if I get a positive number, it means you're walking uphill. If I get a negative number, it means you're walking downhill. So geometrically, a positive number, z is increasing. A negative number, z is decreasing. So looking over here, it says our directional derivative in the direction of u equals, it'll be the gradient vector at 3, -1, dotted with the vector 0, 1. Questions there so far? Well, our gradient vector at 3, -1. 2 times 3 plus 2. 6 times -1.
6.
Always just making sense of everything we're writing. This 2D vector says if you head in the direction of 8, 6, then you're going to walk towards the maximum rate of change. But I'm saying, well, I don't care. I want to walk in this direction. I want to walk straight north, due north. Well, finding the dot product here, which I know we didn't forget, that's the quote-unquote easy one.
Yeah, another dot product.
And I get 6. A positive number, so you are walking uphill, and this is the rate of change. Don't worry, we're going to do it.
It's pretty straightforward. Just don't want to forget steps. That's what it do.
So here I have a surface. The language so far looks pretty familiar. The only thing now it's not asking is the function increasing, it's just asking is the z-coordinate increasing? Same thing. Is the z-coordinate decreasing or increasing at this point in the direction of, now it gave me an angle. Over here we were given a unit vector that points in that direction. So maybe something we remember from physics, any vector can be rewritten as the magnitude of the vector times the cosine of the angle, the magnitude of the vector times the sine of the angle. So we always say, oh, a vector is defined as a magnitude and a direction. Well, if you give me a magnitude and a direction, that means the vector is just equal to the magnitude times the cosine of theta. Magnitude times the sine of theta. For us here, this is just a super quick demonstration. You don't have to write this. This is a unit vector, so a length of 1. Well, then some quick SOHCAHTOA, you can say the cosine of the angle is equal to adjacent over hypotenuse. If we want to generalize this, it's the magnitude times the cosine of the angle. For us here, we want this to be a unit vector. So our magnitude is. So creating the unit vector is as simple as the cosine of the angle, comma, sine of the angle. Again, why is our life so easy there? We want it to be a unit vector. So if they give you an angle instead of the actual unit vector, then it's just cosine of the angle, sine of the angle. Questions? I'll give you guys a 45-second head start. Compute the directional derivative at the point 2, -4 in the direction of this unit vector. My directional derivative is a positive number. So there is one last problem type, and it's not changing much. It's basically the same problem as the first two that we just did, but maybe they give me a direction vector, and maybe it's just a little bit annoying, but they didn't actually normalize this vector, meaning this is not a unit vector. Our definition says it must be a unit vector. So if this is not a unit vector, it doesn't have a length of 1, no worries. You just take 2 seconds and make it a unit vector from our exam 1 knowledge. Find the magnitude, divide each component by 1.
Are you dot prodding each component and dividing it by the magnitude, or?
You're saying to make it a normal vector? Or, excuse me, to make it a unit vector?
Yes.
So you would find the magnitude, divide each component by the magnitude.
Okay.
Now this is a unit vector.
Okay. And would you add those two, or no? You would keep them separate. It'd be x value, comma y value.
It would be x, yes. It would be x value, y value. And say I'm walking in the direction over here, and I want to make it a unit vector. It's still the same direction. We just want it to have length 1. So once you divide them, it's still just x, comma, y.
Okay. Gotcha. Thank you.
All right, so I've got some practice problems here. Just kind of skimming through it. We've got gradient vectors, directional derivatives. Then number 5 is just find the minimum rate of change. So that's just the negative of the gradient. Any questions there? Cool. All right, so sounds like we're going to take exam 2 after spring break.
Boo.
But we will pick back up on Wednesday. Bye, everyone. See you next time.